Hello friends, today let's build on our previous discussions about the four postulates of quantum mechanics and introduce the formalism of quantum operations. This formalism condenses all that we know about the transformations a system undergoes during quantum processes which are allowed by standard quantum mechanics, be it unitary time evolutions or measurements of the system. In this video, we shall present three different perspectives of quantum operations and show that they are in fact equivalent. You may want to check out the previous two videos on the four postulates of quantum mechanics to prepare for this discussion. The links are in the description. If not, let's begin. As before, our main reference is the book on quantum computation and information by Nielsen and Chuang. Check out the link in the description. Here are the four postulates of quantum mechanics. These are the state postulate, which tells us that quantum states are state vectors, or statistical operators, in the case of statistical ensembles. The measurement postulate, which describes how states are transformed after measurements. The time evolution postulate, which describes how quantum states evolve in time when no measurements are made, and the composite state postulate, which tells us how to build a composite quantum system out of single system states, basically by using tensor products and their superpositions. The two postulates relevant to state transformations during quantum processes are the measurement and time evolution postulates. Notice that both the states after measurement or time evolution are very similar in form, both being transformed by an operator and its Hermitian conjugate. This suggests that we should be able to describe both processes under a single formalism. Let's first look at the transformation of a state to a particular measurement outcome, ρm. This transformation is implemented by a set of measurement operators m, which could be arbitrary except for a normalization condition. ρm is normalized with trace equals to 1, and the normalization factor is 1 over the probability of finding the outcome m if the initial state is ρ itself is normalized. This probability is the direct generalization of the Born rule of projective measurements as explained in the previous video. For this expression to be a probability, it must be less equal to 1. This is precisely guaranteed by the normalization condition for the operators m, which we shall review in a moment. Let's kill two birds with one stone by dropping the requirement of normalization, by describing the measurement transformation by the quantum operation em on ρ, where we have simply dropped the factor 1 over the probability of getting the outcome m. The result is that em of ρ carries both the information about the post-measurement state ρm and the associated measurement probability, which is given by its trace. This trace must necessarily be greater or equal to 0, since the transformed state is a positive operator, as guaranteed by its form. If you are not sure why transformations of this form always preserves the positivity of the operator, check out the previous video. The link is in the description. As a probability, this trace must also be less equal to 1. More generally, the operator on the right-hand side can itself be written as an operator sum in a way that is consistent with its positivity. This is an operation describing the transformation of the initial state ρ to a particular outcome m. If a measurement were made, but the system was not selected for a particular outcome for further examination, that is, we are talking about non-selective measurement, then the resulting post-measurement state is obtained by summing over all measurement outcomes. For time evolution, we actually have a very similar transformation, but with the unitary operator ut. This not only preserves the positivity of the initial operator rho, but also its trace. Furthermore, it is easy to see that any composition of time evolution or measurement transformations must necessarily preserve the positivity of the statistical operator. This composition can itself be expressed by some operator sum. Thus we see that all quantum operations could be represented by such an operator sum. We use the term quantum operation to describe any combinations of time evolutions and measurement processes. You may wonder if these cover all the processes allowed by quantum mechanics. We shall answer this question later when we look at a more general definition of quantum operations. An important point worth repeating is that this representation of quantum operations naturally preserves the positivity of the statistical operator. To interpret the trace as the transition probability from the initial state rho to the state ease of rho, we must impose the condition that it is less equal to 1. Let's substitute in the general expression for rho to evaluate this trace. Each bracket is naturally positive due to the positivity of the operators E dagger E. In order to be a probability, the entire sum must be less equal to 1. And for this to happen, the brackets must be less equal to 1, since the sum of the probabilities Pi's is equal to 1. Because the states psi i's in the ensemble are arbitrary, this means the bracket of the sum of E dagger E with respect to any normalized state must be less equal to 1. This in turn requires the operator sum itself to be less equal to the identity operator. Let's look at this in two separate cases. The first is simply an operator equation. The operator sum must be equal to the identity operator. This corresponds to a trace-preserving quantum operation, where if the initial state has a trace of 1, so do the transformed state. But what about the case where the operator sum is less than the identity operator? What could an operator being less than another operator mean? It means that the eigenvalues of the operator sum, which is Hermitian by definition, must be less than 1. This corresponds to an operation that is non-trace preserving, that is, if the initial state has a trace of 1, the transformed state now has a trace of less than 1. We view this trace as the transition probability of the initial state into the transformed state. Thus, the probability interpretation of the trace in the yellow box imposes a constraint on the operator's ease in the blue box. This is the only constraint that has to be satisfied by these operators, which are otherwise arbitrary. And now we have our first definition of a quantum operation, which can be expressed neatly as an operator sum. These operators ease, which implements the transformation, are known as Krauss operators, after the German physicist Karl Krauss. There are actually two other reasonable definitions of quantum operations. One has to do with the interaction of the system with its environment. Here, we define the environment of a system in a general way. It is any other quantum system which interacts with our system of interest. And we consider this composite system as a whole, undergoing the processes of time evolutions and measurements, both on the system as a whole as well as on its individual parts. We then examine the transformation that our system of interest has undergone, and define this as a quantum operation. As you can imagine, this is a very broad picture. Time evolution for this picture is taken to be unitary, and we consider only projective measurements. As we shall see, by sticking with only projective measurements, we do not lose the general perspective. The third definition for quantum operations is simply based on the set of physically motivated axioms. This is a set of general conditions that has to be satisfied by any quantum process. On the surface, this seems to be the most general approach, but we shall prove that all three pictures are in fact equivalent. Let's study the transformation of a system that is coupled to its environment. But before that, we need some preparations. How do we extract the state of a subsystem that is part of a larger composite system? Let's look at a general composite state of System 1 and System 2, which is expressed in some arbitrary basis. We shall consider only a pure state, since a mixed state is just an ensemble of such states. Suppose we are only interested in observing the observables of System 1. Such observables are represented by operators like this one, which acts only on the states of System 1 and leaves those of System 2 alone. How do we obtain an effective state of subsystem 1, such that this state would allow us to calculate any statistical quantities regarding only the observables of System 1? Let's consider the average value of an observable of System 1 with respect to the composite state above. Substituting in this expression, we have by the rules of the tensor product introduced in the previous video, this bracket can be evaluated as the product of two brackets, each belonging to a different system. These brackets can be written as a trace with respect to the bases of System 1 and System 2 respectively. Since the trace of System 2 is just a number, we can bring it into the trace of System 1 together with the rest of the sum. Note the operators within trace 1. They are both operators of System 1, and furthermore, we can bring A1 out of the sum. This operator in the red box ought to be the effective statistical operator describing System 1, such that we recover the usual trace formula of an average value. We can bring the rest of the terms in the red box into trace 2, since these are operators that affect only System 1. As long as we include a tensor product, with the understanding that trace 2 only acts on the states of System 2. Here we cast everything back into cat bras of composite states. The operator in the red box is just the statistical operator of the total composite state. Thus, tracing out System 2 from the composite statistical operator gives an operator that acts on System 1. We claim that Rho 1 is the effective statistical operator of System 1. Let's verify that this has the properties of a statistical operator. Substitute in the composite state, then trace out System 2. Assuming that the basis is orthonormal. This double sum can be factored into two parts. One is just the Hermitian conjugate of the other. We define a new state indexed by alpha. This state may not be normalized. And we end up with a sum of cat brows, which are obviously positive operators. Thus row 1 is indeed positive, as a statistical operator should be. Rather than going through such explicit calculations, we can in fact see the positivity of row 1 straight away. Just evaluate this trace with some basis in the state space of system 2. Then we ask the question, what is the bracket of row 1 with respect to an arbitrary state of system 1, using the expression in the red box? Since the total composite state is a positive operator, all these brackets with respect to composite states of 1 and 2 must also be positive. Thus we can see that row 1 is therefore a positive operator without really doing any calculations. Furthermore, if we take the trace of row 1 over system 1, the result must be equal to 1, as long as the total composite state is normalized. These two properties show that row 1, which is obtained after tracing out system 2 from the total composite state, is indeed a statistical operator of system 1. Thus we have shown how to obtain the state of a subsystem from a total composite state, which effectively allows us to calculate any statistical quantities of this subsystem, like the average value of an observable in this example. This is all done by taking a partial trace, where we trace out the system that is not of interest, such as system 2. There is an important point we would like to make about the partial trace. But first, let's simplify the notation for the composite state. Often, we will simply hide the tensor product symbol. Suppose we take this partial trace in a particular basis of system 2. The states in this basis can themselves be expressed in terms of an arbitrary basis. Furthermore, these two bases are related through an unitary transformation if both of them are orthonormal. By the definition of unitary matrices, the expression in the red box must be equal to the Kroneker's delta. Thus we see that the partial trace evaluated in these two different bases are the same. The partial trace of a composite operator is therefore basis independent. This is an important result that is often used in quantum mechanics. And it makes good physical sense, since oftentimes we are only interested in a subsystem that is part of a larger system, and may not be able to keep track of all those other parts and monitor what happens to them. This result tells us that we need not worry about such details, since we will get the same state for the subsystem of interest. Now we are ready to examine the interaction of a system with its environment. We shall show that this picture will provide a definition for quantum operations that is equivalent to the operator sum representation. Suppose the system of interest is in an initial state described by rho, and its environment can also be described by some statistical operator. For the sake of simplicity, Let's assume that these two systems are not initially entangled in any way and can be expressed as a tensor product. Later, we will show that this assumption will not actually affect our final result, and the initial states could actually be entangled. But first, let's explain what we mean by the tensor product of two statistical operators. We can expand this product explicitly with the definite expressions for the statistical operators. This tensor product can be written as a ket-bra of product states between the system and its environment, while this product of probabilities is actually another set of normalized probabilities, as we can easily see. So this tensor product of the statistical operators of system and environment is just an ensemble of product states between the two systems. Now let this composite system undergoes an unitary time evolution, with the time evolution operator generated by the total Hamiltonian of the composite system. The omegas here are numerical constants. In general, these two systems will be interacting with one another. This is the situation where both the operators A and B are not equal to the identity operator. After some time, a projective measurement is made on the composite system. Let's assume that this is some kind of a selective measurement where we have selected a particular outcome M. This corresponds to a measurement of some observable of the composite system, which is represented by basis A. After undergoing all these processes, the initial state rho is probably entangled with its environment. Now we wish to extract the state of this subsystem. This is done by tracing out the environment. Thus the initial state rho is transformed into this final state. We can define a quantum operation as such a transformation. The processes just described closely mirrors how we actually observe a quantum system. Note that this transformation is obviously linear. This is an important point that we shall return to later. Since the details of time evolution is not relevant to our discussion, let's simplify our notation by hiding the time arguments. Now we will show that we can use this transformation to replicate any quantum operation on rho that has an operator sum representation. Let's assume that rho is some general state. Due to the linearity of the transformation, we need only to study the case of a pure state. Now let's look at the state of the environment. To make things easy, let's choose a simple initial state for the environment. Just some pure state E0. As before, we can write this tensor product of ket-bras as the ket-bra of a product state. Now let's look at the unitary transformation of the initial state. We require U to effect such a transformation. The states MKs are a set of orthonormal states of the environment, while the operators EMKs act on the states of the system. To give a definite example, these operators represent the quantum operation describing a measurement process that led to an outcome M. But of course, this could be any operator sum representation of any quantum operation, which is what we are trying to simulate with a system coupled to its environment. For this equation to be consistent with the unitarity of U, the right-hand side must be a normalized state. If the initial state is normalized, using the orthonormality of the states mk's. We require this sum to be equal to 1 to respect the unitarity of U, which can only be satisfied for an arbitrary state psi alpha if the sum of E dagger E's is equal to the identity operator. This is just a condition that has to be satisfied by the Krauss operators for a trace-preserving quantum operation, which is a non-selective measurement. As we have explained in the previous video, a non-selective measurement is simply the sum over all the possibilities that corresponds to each outcome. The particular outcome we get is a selection out of all possibilities. This condition in the yellow box has to be satisfied as long as all the possibilities are accounted for and the probabilities sum to 1, even though in the present run of the experiment we get this particular outcome M. Therefore, the right-hand side of this equation is consistent with the unitarity of U as long as the condition in the yellow box is satisfied. Next, we consider the projective measurement. We use this measurement to select out the environment states Mk that have a particular value of M by using the orthonormality of these states. This will correspond to the outcome M of the operator sum. Finally, we traced out the environment. Let's use the Mk states as the basis. These states belong to system 1. While these are inner products between the states of the environment. We can use the orthonormality of the Mk states to evaluate these. They impose the constraints M double prime equals M and K double prime equals K prime equals K, which gives the following. Thus we see that if we couple a system to its environment, let this composite system evolve in time and make projective measurements on it, then isolate the original system again, we can effectively simulate any quantum operation on the system that can be represented by an operator sum. Although we have used the specific example of a generalized measurement with the particular outcome M, it should be clear that our result is quite general. Depending on whether there are multiple values of M or just one value, the trace of the transformed state could take any value between 0 and 1. Therefore, unitary time evolution plus projective measurement is equivalent to the operator sum representation of quantum operations, as long as we are willing to enlarge the system to include part of its environment. But wait a minute, some of you might wonder, isn't it more accurate to say that what we have just shown is just that the operator sum representation is a subset of processes where a system is coupled with its environment? They are not really equivalent. One encompasses the other. Actually, they are in fact equivalent. The easiest way to prove this is to introduce the third picture of quantum operations, which is based on the most general considerations. This approach is based on a set of physically motivated axioms. This definition is so broad that it could include both of our previous definitions of quantum operations. We will then show that this new definition of quantum operation has in fact an operator sum representation. What this implies is that the system coupled with the environment picture contains the operator sum picture, which in turn contains the axiomatic picture that encompasses all the other pictures. This will effectively prove the equivalence of all three pictures of quantum operations. Let's now introduce the physical axioms. The first axiom is that the trace of the state transformed under a quantum operation must take values between 0 and 1, like a probability. This feature is explicitly built into the operator sum representation. As a condition on the Krauss operator's E case, for the case of a system coupled to its environment, we have shown earlier that this trace condition is satisfied by both projective measurement and unitary time evolution. The question remains whether the partial trace over the environment would preserve this property. The answer is yes, since we have shown earlier the partial trace preserves the positivity of the statistical operator. And taking another trace on this positive operator will turn it into a full trace of the composite state, which, as we have said, satisfies the trace condition. Therefore, axiom A1 is satisfied by both previous pictures of quantum operations. The next axiom is the linearity of the map. Quantum operations are linear transformations. Before we justify this property, let's first understand what's in the argument on the left-hand side of this equation. This is an ensemble of statistical operators rho i's, which is itself a statistical operator. Let's see. Rho I can be written in the standard form. Note that the reason why the index A is itself indexed by I is because each of the operator rho I may contain a different set of states and probabilities. Substitute this into our ensemble. Notice that the term underlined blue is a composite set of probabilities that sum to 1. Thus, indeed, we have a statistical operator in the argument on the left-hand side of the equation above. It is obvious that both our previous pictures of quantum operations satisfy this linear property. But let's justify this property physically. To give a definite example, let's assume that this is a transformation that gives us the outcome M from a measurement. For each member of the ensemble, rho I, we have. This happens with the probability Pi. Thus, the normalized state that corresponds to the measurement outcome M for the ensemble rho is given by. This normalized state of the ensemble after measurement can be expressed in terms of the post-measurement states of its members, rho i's, which are also normalized. Let's justify this relation. The conditional probability underlined yellow is the probability that, having measured an outcome M, what is the probability that the state we were given before measurement is in fact the state rho I out of the ensemble. In other words, this is the probability of occurrence of the state in the blue box. Thus, the expression on the right-hand side of this equation is in the standard form of a statistical operator. This is the statistical operator that corresponds to the outcome M, and so is equal to the left-hand side. We can rewrite this product of probabilities using the Bayes rule. Let's start with the joint probability that we will get row I from the ensemble and also measure the outcome M. This is equal to the probability of getting M multiplied by the conditional probability of getting row I given M by the usual rules of probability. Note that this is just the product above. Alternatively, this is also equal to the probability of getting row I multiplied by the conditional probability of getting M given row I. We shall substitute this last expression above. Thus, we have shown that a quantum operation is necessarily a linear map. This is simply implied by the Bayes rule. The last axiom is less familiar, but rather obvious. If you perform a quantum operation on a subsystem that is part of a total composite system, leaving alone the rest of the composite system, the total system should remain as a valid state, that is, a positive operator. Any map E that satisfies this property is known as a completely positive map. Of course, the map E by itself must be a positive map to begin with. Just to be clear, I here is the identity map. It leaves any operator unchanged. Here we use an arbitrary cat bra as an example. We are interested in System 1, while System 2 is the rest of the composite system, which is left alone. For an example of the transformation above, let's use a general composite pure state, which corresponds to this statistical operator. Now perform a quantum operation on System 1. Here we see that any implementation of a quantum operation must be able to act on an arbitrary cat bra. Let's use the operator sum representation for this quantum operation. We can test if this is a completely positive map. Let's see if this transformed composite state is positive. We can bring the Krauss operators outside. Since the total composite state is positive and is sandwiched between pairs of operators and their Hermitian conjugates, which preserve positivity, the transformed state is also positive. Therefore, the operator sum representation is a completely positive map and satisfies the third axiom. As for the case of a system coupled to its environment, the positivity of this picture is apparent if we look at things in this way. We have the system and its environment from the original construction, but the environment is extended by environment prime, which is just a spectator and is not involved in any interactions with the other two systems. The unitary evolution and projective measurement act only on these two systems. And in the end, we traced out the original environment. This composite operator left in the end must necessarily be a positive operator, since none of the processes involved will affect the positivity of the initial state. Not the unitary evolution, nor the projective measurement, or the partial trace. Therefore, quantum operations, as defined by a system coupled to its environment, is also a completely positive map. Note that these tensor products refer to the tensor product space of the three systems, and not just their product states. Rather, it contains any possible superpositions, including entangled states, so our result is quite general. You may wonder, How could such an obvious condition, like axiom 3, allow us to pin down the representation of a quantum operation? This is what we will show next. Using these three axioms, we shall prove that any transformation that possesses these properties has an operator sum representation. This will close the circle that demonstrates the equivalence of the three pictures of quantum operations. Due to the linearity axiom, we need only to consider the transformation of pure states. To begin the proof of this statement, let's start with the composite state capital Psi. This is an entangled state between System 1 and System 2. As usual, we are interested in System 1, which is the one undergoing the quantum operation above, while System 2 just represents the rest of the composite system. We shall leave these alone. It is there simply to help us prove some general properties of quantum operations on System 1, which is itself arbitrary. Psi i's are a set of orthonormal basis states for System 1, while tilde psi i's are also an orthonormal set of states, but of System 2. These need not be a complete basis for System 2, but the number of states must match those of the basis of System 1, which is to say, System 2 must be larger or equal in size to System 1. We can express the state in the quantum operation above in terms of the basis psi i's. Let's perform this quantum operation on the composite state, leaving System 2 alone. Now let's define the state tilde psi of System 2 in terms of tilde psi i's, which has coefficients that are the complex conjugation of those of the state psi. We then use this state to calculate the bracket of the transformed composite state. This is a partial bracket involving only System 2, which we indicate by the subscript. Using the result above, we have this is now an operator of just System 1. Using the linearity of the quantum operation, we have the result is equal to the quantum operation on state psi. E is a positive map, therefore the left-hand side of this equation is also a positive operator. Axiom 3 requires that the transformed composite state within the bracket must also be positive. Therefore, all its eigenvalues lambdas must be positive. The states case are its eigenstates. The subscript 1, 2 is just to remind us that this is a composite state. Substituting this into the partial bracket, we have this is another way to express the transformation of psi of System 1. Let's further expand this last expression. Substituting in the expression for tilde psi. Let's define this partial bracket as some state ki of System 1. This term is simply the Hermitian conjugate. Notice that this term in the green box is completely independent of the state that the quantum operation E is acting on, which is psi. This information is carried by the coefficients alphas. This is an important point. Take a moment to recall where the green box came from by looking at the red boxes. Using the linearity of E, we can bring out the alphas explicitly. The action of E on the cat bra of the basis states psi I and psi j can thus be identified with the operator in the green box. This also shows that once we know how the quantum operation acts on the basis, the transformation of any state would then be determined. It is not difficult to see that the green box can be written as a transformation by an operator sum, where the Krauss operators EKs are defined by this equation. In this way, these operators are completely independent of the specific state psi, as they should be. By showing that a quantum operation on any basis can be expressed as transformation by a set of Krauss operators in an operator sum, using only our physical axioms, we have proven what we have set out to prove. Any quantum operation that satisfies the axioms has an operator sum representation. Thus we have proven the missing link that establishes the equivalence of the three pictures of quantum operations. The picture of a system coupled with an environment seems to be the most intuitive, since it is based on unitary time evolution, which itself is generated by a Hamiltonian. Much of what we know of fundamental physics are built on such objects, from the hydrogen atom to the quantum fields of the standard model of elementary particles. All these started from the formalism of the canonical quantization of classical physics pioneered by Paul Dirac, which provides a definite link between classical physics and quantum mechanics. Once we have a model of how a system interacts with its environment, we could proceed to derive from it an operator sum representation of the state transformation, which is much easier to apply. We shall provide more examples of this in future videos. Now you know why we stick to unitary evolutions and projective measurements in most of our discussions. Not because we are oversimplifying matters, but rather, this formalism is in fact broad enough to encompass all quantum operations. If you like this video, consider giving it a like and subscribe to this channel. And remember to press the notification bell so that you'll know when a new video is ready. See you next time, and thanks for watching.